Okay, so so today we're going to talk about integrals of trig functions. We did derivatives of trig functions. I hope you remember some of them, right? Derivative sine is what? So today we're going to talk about integrals. Oh, okay, sorry. I was trying to. I hope you remember some of them. Right? Derivative sine is what? Okay, I was trying to do it. Okay. Right here. Okay, I was trying to do it. Okay, oh, right here. Yeah, you just click right here. Where it says right now. Okay. What's that? Okay. Right here. Is right here, and then like that, it just moves it. Okay. Okay. Great. Thank you. Okay, I was first. I'm trying for the first time. Okay, and then your face will not show there unless you want to want to be shown. Okay, since if that works, then I don't have to load every time. Okay, I will see what it works. So I hope you at least remember the derivative sign is what? Cosine, right? Derivative cosine is negative sign and so on. And the derivative of tangent is secant square. So those three should be remembered. But today we're going to look at the inverse process of differentiation. So, so we'll be learning the integral formulas for trig functions and review some rules. In particular, those are 6 trig functions and some additional formulas. Okay, so here, this is something I want to review, that we learned that whenever you have a integral formula, you can rewrite it in 3 different but equivalent way. So here, for example, in the middle, simply says that, big F is the antiderivative of little f, or little f is the derivative of big F. You can rewrite it in this integral, in-depth integral form, which is to say that the in-depth integral of little f is capital F, this particular antiderivative plus c. Or you can write that the differential of the capital F is the product of its derivative, which is little f and the dx. Okay, these 3 are exactly the same. Well, in terms of what they mean. Okay, so here's an example that I gave you earlier. Okay, if you want to integrate x squared, you can use the formula, right? But if you want to verify this formula, you can differentiate, the right-hand side of the function on the right-hand side to say whether its derivative is exactly x squared, and we know that is the case. Or you can use this differential form, which is just a slightly different way, but equivalent to the derivative formula. Okay, so now we're going to look at the trig functions. Whenever we have a trig derivative formula, we can rewrite it as into integral formula. And we just reviewed 2 of them, right? Okay, so we're going to do exactly that for each of the 6 derivative formulas. Okay. So here, this is again, this is the one we're going to use. I just rewrite it slightly different way, order. So for example, we know the derivative of sine is cosine, right? Which means if you integrate cosine, you get the all, antiderivative cosine, it will be sine plus c. Okay, make sense? So here, the capital F is big F. Little f is cosine, and we just rewrite the derivative formula in the integral form. And you can do this for every other formula with a possible minor, change. For example, the derivative of cosine is negative sign. So which means if you integrate sine, you get a cosine. But in order to have a formula, we prefer to not have a negative sign, you know, in the integrand. Just wanted to have a formula for the integral of a sign. Well, if you integrate sign, you will get negative quotient. Okay. Now this is same as this. You can, if you wanted to get a derivative, get sign as a derivative, so this is the same as negative quotient x equal to sign, right? Okay, so sometimes you wanted to have a exact function as your derivative, okay, or your integrand. You can change your sign, or you can multiply both sides by a constant. Okay, so the purpose here is we wanted to find an antiderivative formula or integral formula for those common functions like a sine, cosine. Okay, but we wanted to start with a known formula, integral formula, derivative formula. So the next one, which is also should be remembered, is the derivative tangent is second square. There's a square here, which means that if you integrate the second square, you get a tangent plus c. Okay. So all of those formulas are very easy to get, very well, almost free. Okay. So those are the most important, well, three of the most important trick in integral formulas. And we have three more, right? We can just recall them and rewrite them in integral form. That's what we will do. Okay, so let's finish this exercise. Okay, next one is the derivative of cotangent, right? It's negative cosecant squared. Again, here we can rewrite this as the integral of cosecant squared is a negative cotangent. You know, we could put a negative sign in the front, but this is more convenient for application. Okay. So not surprisingly, you can get all of the six. Okay. Integral of secant is the product of secant and tangent. So if you integrate the product, the derivative, you get the you get the function itself plus c. Okay. And finally, the derivative of cosecant is negative cosecant times cotangent. So if you integrate the product on the right hand side, you get a negative cosecant x. Okay. Now here you can actually summarize a more general fact. So if you have this, if you integrate the derivative of a function, you will get the function itself plus c. Okay, this is true for any function. Okay, so capital F could be, you know, a trig function or any other function. So okay, so we have immediately get 6 formulas. Now, of course, you know, if you are given a problem on only if the given integral is exactly one of the 6, you can use those formulas, right? Okay, so if you are not, you have to use other, you know, formulas and integration rules. Okay. So let's look at some. Okay, so this is another table, and I wanted to tell you what the difference from this table and the 6 formulas that we get. The first 3 are exactly the same as what we got. Well, actually, first 2, I'm sorry. Okay, we get integral sine and integral cosine. Okay. The only difference for the first 2 and those is that we changed it from x to u. The reason is that later we will use u substitution to solve a more general, you know, integral problem. So we find it's easier, maybe more convenient to use the variable u for the integral variable. But the first 2 are known. The other 4 are not known yet, but I can tell you what they are and why they are here. Well, the other 4 functions, they are in the integrand, they are tangent, cotangent, secant, and cosecant. Okay, so there are the 6 functions. We would like to know what will be their, you know, the and the derivatives. Okay, because the previous 6 formulas do not tell us which functions have those 4 trig functions as their derivatives. Okay. So it turns out we have those 4 formulas. And how do we verify those? So here there are 2 ways to verify this. We can just use the fact that we used to verify those formulas. That would be easiest. Okay. Or we can try to find them using the like a substitution or other methods to do it. Okay. So let me give you an example here to show you how to verify the last 4 formulas. Okay. It's actually pretty easy to do. Let me give you an example. Take this as an example. Okay, this is the same as the derivative of the right-hand side, which is log derivative log of this second u plus, actually it should be d over du, since we're using u as the variable, equal to second u. Okay, so what's amazing here is that the integrand is simple, just a second u, but the derivative is complicated. It involves log, absolute value, the sum of a second tangent. So if we wanted to find it directly, it's going to we will use some kind of tricky substitution. But if we are given this formula, we just want to convince or confirm that it's true, is much easier. Just to differentiate this function on the right-hand side and to say whether the derivative is exactly the integrand. Okay, this can be done for all of the 4, even the 6 functions, 6 formulas. Okay, so let's. But one thing you can notice that all of those derivatives involve log, right? Involve log. So let's check that. So here's an example. I wanted to verify this is the formula. Now here I change the variable to x again. So let's do that. So here again to check the derivative of this guy on the right hand side. Okay. Now, in order to take the derivative of log, composite log, we're going to use this formula. Here's the formula that when you take the derivative of log of x, you get 1 over x, right? But if you have a composite log function, so it's like a d over dx log of g of x, it's equal to the derivative of the function g divided by the function itself. Okay, that's the formula we have, we learned before. What's really amazing here is that for log function, we know log is defined only for positive input, right? So if g is negative, this would not be defined. But you can take absolute value of g before you take a log. That will extend the definition of the domain of this function. But the interesting thing here is that even you take the derivative log of absolute of g of x, the derivative is still the same. Okay. Now remember this fact, if you take the log of x, you get 1 over x. This is true for all positive x. But if you take the absolute value first, then this will be true for all x. So here for all x not equal to 0. And from this simple formula, you can use the chain rule to verify the formula above. Okay, that's something we're going to use here. So here we're going to do this. We're going to use this formula and get the denominator is second x plus tangent x. Okay, that's our g. The numerator will be the derivative of this inside function here. So second x. I'm going to take a derivative of each one because the function here is a sum. So let's take a derivative of secant and tangent and divide it by their sum. Okay, now, so here you need to remember the formula for the derivative of secant and tangent. Okay, we recorded at the beginning. So anyone remember derivative of secant is what? You can check your notes if you are taking notes. What's the derivative of second x? Okay, just read it out if you have found it. Anyone? Okay, second times tangent. Okay, that's good too. How about the derivative of tangent? Anyone remember? Derivative of tangent is what? Second square, yeah. So you see here, it's interesting and saying here is that both derivative involve second. So second is a common factor. So let's simplify it by taking it out. So get a second x, and then what's inside is tangent x plus second x. Did you see something really interesting here and helpful? After second is taken out, the inside is tangent plus second, which is exactly the denominator, right? Okay. So you can see the second x is the derivative of this function. Okay, so we have verified that the truth of this formula. Of course, the harder part would be if we are not given this formula, how do we find it? Well, in fact, in the book, it uses kind of a special substitution to determine this one. In fact, the substitution will be just the sum. So we have already done this example, but we can also find it by use a substitution. U equal to second x plus tangent x. Then you will become, we have to convert this one into log integral 1 over u. You can look at the book if you are interested. Okay. So that's I think that's a choice in life. If you want to verify something, it's easier than discover something, right? Okay, any question? Okay, you can do this for all of the other four formulas. So let's now talk about if we have to use a substitution. We cannot use one of those 6 formulas, or actually more than 6 now. We have a total of 10 formulas today, 10 integral formulas we learned today. Okay, but suppose you have a function that involves a trig or not, but you have to use a substitution. Okay, this is a very short summary on when you can use a substitution. Okay, typically a substitution means you are going to set a u equal to a function g of x, and to simplify our integral. So suppose the integral that we are given is the integral of integrand, a function of x times dx. That's something you wanted to evaluate. Okay. Okay. So when does the substitution work? Well, the general condition is that the integrand, which is a function of x times dx, has to be able to written as some number k, which could be 1, times a function of u times du. Okay. If this is the case, then it's going to work. Now, what's the du here? Du here is it's just a differential of u, so it's a product of the derivative g and dx. Okay, so this is general principle, and here are 2 most common examples. So if your integrand is the product of a composite function with g of x be inside and the derivative of g, then you can see u equal to g of x will be perfect. If you have a u equal to g of x, then you have the composite function is just f of u, right? And this derivative of g times the dx is just du, and this is u. So immediately you can see the simplification. Okay. A slightly more general case is that you may not see the derivative of g right there. Okay, but you can see that the product of h of x and dx is proportional to du, which is g prime dx. then that's also work. Okay. This actually is pretty common. Okay. So the way to look at a substitution is this: whenever you see a composite function in the integrand, and you should immediately think about u equal to g, that inner function. Okay. Unless you already have other ways to get the the integral quicker. Otherwise, you can think u equal. What happens if u equal to g of x? Whether you can relate, the remaining part with du. Okay, if you can, if you have there's a, you can write the remaining part as du or du times a constant k, then you're in good situation. Okay, so let's look at some examples here. Okay, how about this guy here? Okay, here we have our integral that's 3x squared and sine x cubed. So you see, it is a product of two functions. Okay, the first one is a polynomial. The second one is a composite trig function. So you see there is a composite function, and obviously there's no simple formula that can give us the antiderivative. Whenever this is the case, or whenever I needed to try to use a substitution, I always do this. You can try this too. I always rewrite the integral so that the composite function or composite function factor goes first. So that's, and then the remaining thing, whatever it is, goes second together with dx. Okay, and now wanted to see, wanted to try, try to, so this is something we need to try u equal to x cubed, right? And then we need to calculate what's du, whether du takes care of the remaining, the factor of the integrand and dx. Well, if you take it from du is the derivative. The du is the derivative of this function u, so it's a 3x squared dx. Well, that's exactly what we have, right? So I mean, of course, we are giving this example, but you see, so this works. So this is a du, so that's what we're going to do. So this may be done by heart, or you can do it on your scratch paper. But when you write the solution, you just write it nicely like this. So let u be x cubed, and then du is 3x squared dx. And so the given integral, which is x squared, you can write the original one or write the one that we just have rewritten. It's going to be sine of u and then du, right? You can see that the sine of x cubed is sine of u. 3x squared dx is du. Okay, that's why it is actually easier to recognize, to work out if you have rearranged the order of the factors of the integrand. So far okay, right? So we converted to sine of u du, and that's something we can use the formula, right? Okay. Now here's the question: what is the formula for the for antiderivative sine of u? Okay. Anyone remember integral sine x equal to what? Cosine or negative cosine, yeah. So here it's u, so it's a negative cosine u plus c. Don't forget plus c. The reason we plus c is that the antiderivatives of a function is not unique. It has infinite many antiderivatives which are different by constant. So this is a integral of this new function, but we needed to convert the function in terms of x. So get this. Okay. So we get this answer. Now, if you are curious whether you get the right answer, you can actually check by using the formula. The check step is not necessary. It's fun to do it. I think it's also satisfying. you can check that the derivative of this guy is going to be exactly, the sine x cubed times 3x squared. Because you need to use the chain rule, right? The derivative of cosine is a negative sign, so the negative sign will be canceled. You will also get, the derivative of x cubed, which is 3x squared. So that's the same. So you can always check if you want. Okay, so that's an example for substitution. Whenever you see a composite function as a factor of the integrand, you can always try to set u to be the inner function of the composite function. Okay. Okay. I will again skip one and go to this one here. So here we are given something pretty complicated. The integrand is sine 4x squared times cosine 4x dx. Okay, so in this case here, it's not that hard to tell that there's a composite function, which is the first factor, and there's another function, another second factor. And so because using formula is the easiest way to evaluate integral, the second, the next one, next easiest on the list will be by substitution. So let's try that. So here, again, by heart, you can try to see whether the derivative of the inner function, so set u to be sine 4x. Okay, then let's calculate du. Du will be the derivative. Okay. So we need to use chain rule. The derivative sine is cosine 4x. But remember, this is not a sine x, but a sine 4x, so it's a composite function. So we need to multiply by the derivative of the function inside. The derivative of 4x is 4, and then dx. Okay. So notice that here, the du is not exactly what we have, in the integrand. Okay, we do not have a factor 4 in the integrand, but that's okay. That's the difference is a constant factor. So here, for example, you can write this as because you have cosine 4x dx that needs to be converted. So you can solve for this this combination here, which will be 1/4 du. You just divide both sides by 4. You can get what you need to convert. That's one way to do it. Yeah, so some people can use another way, which is a little bit shorter. So it's up to you. Okay, I will show you that if you prefer another way to do it. But anyway, this check shows that u equal to sine 4x will simplify this integral. So again, you can yeah, you can include this part in as part of your solution, so you don't have to rewrite it. But sometimes your first attempt might not work, so you have to scratch it and try it again. So let's pretend that this is not our first attempt. So but we figured out this works. So we said u equal to sine 4x and du is a 4 sine cosine 4x. So let me just rewrite it slightly differently. Okay, and you can now solve for cosine 4x dx. And so here, okay, this will be integral of a sine of u. Oh, actually, it's simpler than that. There's no more sine, just the u squared, right? And then 1/4 du. So you can see it is converted to a power function. Okay. And some people use another way, which I also like to, is this. So here you can rewrite this as sine 4x squared. Now, because du is 4 times cosine 4x dx, so you can put a 4 here. Just make it du here. But because there was no 4 from to begin with, so when you multiply the integrand by 4, you need to divide it by 4 outside. So that's another way to do it. Okay, so this will be the same as 1/4 integral u squared du. Okay, so you can do this. But anyway, the result is the same. So you get 1/4. That's a constant coefficient. For u squared, what's the antiderivative? How do you find u squared? What's the derivative of u squared? Is that 2u, right? Sorry, I tricked you. It's not 2u. It's a u cubed over 3. That's the derivative would be. Okay, the derivative will be 2u, but antiderivative u cubed over 3 plus c. And so that's 1/12. And u is sine 4x. So we could write the exponent over the function name. So that's a answer. Okay. Yeah. Okay, so that's another example. So we see substitution is really a pretty useful one. It immediately simplifies the function you're given if the substitution works. Yeah. Okay, so we're going to skip some examples. We wanted to I'll give you a formula as a special substitution that works so well, okay, which is when you have a integral where the integrand is a function composed with a linear function. Okay, this is the case that a substitution u equal to the linear function always work. Okay, if the integrand is a function composed with a linear function without any other function as the other factor, then this will always work. Okay, because the derivative of u is a constant. Okay, but in this case, you can set u equal to linear function and work out simplify the integral first, and use the formula to evaluate the integral. That you can always go through that process, because this process, you know what is the result. Okay, the result will be 1/a, the coefficient of x, times the integrand, the antiderivative composed with the same linear function. You can remember this formula. So for example, if you integrate tangent 4x, what do we get? Well, you might want to recall that what is the integral of tangent x. Okay, we already learned this formula, even though I do not expect everyone to remember it yet. The integral of this one is negative log of cosine x plus c. Okay, so of course you say, well, I've not remembered this one yet, but that's okay. You can put those harder remember formulas on your cheat sheet, but you know this fact. You need to use this formula no matter you use substitution or this formula. So to use this formula, how do we do? Well, it means so this would be our capital F. This is our capital F. So this formula tells us the integral of tangent 4x is going to be 1/4, right? Times this antiderivative negative log cosine x, but x has to be replaced by 4x plus c, like that. So you can write out the answer right away. Okay. Of course, here you can rewrite it as negative 1/4 log of quotient 4x plus c outside. So you can do that. Okay. So similarly for the second integral here, okay, if you know the formula for the integral of second x, you can write out the integral of second 3x minus 5 or ax plus b. You know, that's so here. Okay, I will write this answer in later so that I can check. But you can do it. So here you need to remember what is the here I can write it here. Yeah, actually I do not need to write. We need to use that formula, right? Okay. So let's use that formula. We can write the answer right away. So it's going to be 1/3 because a is 1/3. A is 3, and then I have a log of a second u. But u is 3x minus 5 plus tangent u, so it's tangent 3x minus 5, and then x value plus c. Okay, so you can write it right away. Okay. Well, this is something I really find it's handy because when you solve a problem, no matter in real life or in a test, you wanted to balance the time you spend and also the accuracy, right? So you wanted to spend the time only if it is necessary to get the right answer. If you can do something quick, you can take advantage of some formulas or some shortcuts. Okay, so let's continue. Okay, so let's look at the last method here, which is tabular method. I think we know that pretty well. It is so nice when you have an integral of the right form, and that happens here. So you might remember when you integrate a product of a polynomial, an exponential function, you know, e to a number times x, you can use a tabular method. Interestingly, it also works if you have an integrand where you have a product of polynomial and quotient ax or sine ax, where a is a number, and you can also you know, use this method. Okay, let's see how does it work. So we're going to use this example here to work to figure out. So remember the method of tabular method. Okay, so first we need to make sure this is the right form, and the two factors will be used to form the top row of a table. So in this case, the polynomial will be the first factor, so it's 3x. And then the trig function or exponential function will be the second column, the top of the second column. In this case, the quotient 4x. Okay, now we're going to complete this table. And for the first column, we're going to keep differentiating. And so when you differentiate 3x, what do you get? Derivative of 3x is what? 3, okay? And then continue to do that. Derivative of 3 is what? 0, okay? So because you have a polynomial as the first factor, sooner or later, you're going to get a 0 derivative. Then it's time to stop. Okay, now for the second column, we need to integrate the second factor. Okay, so we need to start with integrating. So let's do this. This one here should be integral quotient 4x. Okay, now here, can you evaluate this or find this the integral quotient 4x? How do you do it? You can use a substitution, right? Okay, or use the formula we just talked about. Okay, the integral quotient is a sine plus c. So this will be 1/4 sine 4x. Okay, so you can see, you can write this formula right away. You could use a substitution, but it's going to take you some time. Okay, so we get the second entry here is 1/4 sine 4x, and then the next one will be, we need to integrate this again. Okay, you do not need to write out this integral if you know what you're evaluating. But when you're evaluating this integral, integral of a sine is a negative quotient. So you're going to get a negative 1/16 because you're going to 1/4 times 1/4. You always have a negative sign. And then you have a quotient here. Okay. Sorry, I think I needed to redo this one here. So this is equal to negative 1/16 quotient 4x. Okay, now here notice that we do not put a c here because we only need a one function for the entry, just one and a derivative of quotient 4x and so on. So that's why we take a capital C to be 0. So now let's use the tabular method, which says that this is going to be the integral of the product of the top row, okay, is equal to the combination of those diagonal products. Okay, so we have two products in this case. Okay, so I have the 3x times 1/4 sine 4x. That's the first product. The second product would be negative 3 times, be careful here, the negative sign for the second term is part of the formula. So it's 3 times negative 1/16 quotient 4x. Okay, we still get two products. We combine them with plus minus signs here, and then we add a c to it. That will be the answer. So we can simplify this one as 3/4x sine 4x plus 3/16 cosine 4x plus c. Okay, so that will be the result. Okay, now if we are interested, we can differentiate it, then take a derivative function. There will be exactly 3 times quotient 4x. Okay. The derivative one is it takes a little bit of time because for the first term we need to use product rule and chain rule and so on. So, but the derivative will simplify to the given integrand. Okay, so we will have a couple other examples. I think we have learned a lot today. So let's stop here. If you have any question, you can ask now, or you can come here to ask me. Okay. Hello.
I'll ask my exam papers.
Oh, you mean have not picked up your exam? Okay. Are you okay? I haven't seen you for a while.
Yeah, I just I join on Zoom
Oh, okay.
most times, but it's just because of either the weather is like too cold or is either the weather is too cold or I'm sick.
Oh.
So I just end up not coming.
Okay. Okay, I will Emerita and Orlando, Shady. Okay. Yeah. Okay. Okay. Yeah. Okay. Good. And I will.
Exactly.
Yeah.
Let me take it.
Okay. Yeah, that's apparently there's some problems. The other day there was a student who came to ask have the same problem. So I mean, typically when I extend it, you should be able to retake it, but I don't know why. There's some issue with the system. So in that case, I can either extend it for you to try again, or you can. Have you written down the answers?
No.
Okay.
I wasn't even able to like.
Oh, okay.
It says
Yeah, okay. Can you send me a message to inbox again? I will try again. If not, then we have to find other ways like a printout or something. Yeah. Okay. Okay. Yeah.